All right, so we're going to continue with example 4.9. We found the initial speed of the ball at the second hole. So now we're going to do the initial speed of the ball at the fourth hole. Okay, so it's going to be the same process. So V naught is going to equal the square root of, and again, he's going to be shooting at 90 meters. Okay. And so R times G, 9.8 meters per second squared, divided by sine of 2 times our angle. And at this shot, he's going to do 70 degrees. Okay, so square root of all that. So let's plug that into our calculator. And we get our velocity is 37 meters per second in this case. Okay. So now that we have our initial velocities, our initial speeds, we want to write the trajectory equations for both of these cases. Okay. And that equation is back here. So y equals tan theta naught x minus g over 2 v naught cosine theta naught x squared. Okay, so let's go back. Okay, I'll put it on this page. So I'm going to just say y1 for the first case is tan theta naught, which was 30 degrees, and that's times x, I believe. Yes, minus g, oops, minus g over 2 cosine, sorry that I'm going back and forth, cosine 30 degrees, and then v naught, which we found was 31.9 meters per second in this case. And I think that is it. Yes, I believe so. Yes, okay. Times x squared. Okay. This is going to be 9.8 meters per second squared. Okay. So, is that? Yeah. Okay. Just wanted to triple check. Okay, so first I'm going to say tangent of 30 is 0.58 approximately. X minus, we have 9.8 divided by 2 times 31.9 times cosine of 30. And so that is 0.18 x squared. So this is my y1 of x. Now y2 of x, I should say, is going to be tangent of, I think it was 70 degrees. 70 degrees. X minus 9.8 over, let's see, 2 cosine 70 degrees times 37, I believe it was. Yep. Okay. So tangent of 70 is 2.7 approximately, minus 9.8 over 2 times 37 times cosine of 70, which is 0.39 x squared. So now we have our two equations that describe the projectile, okay, or the trajectory. And it asks to graph both of these trajectories. I'm not going to do that, but I'm going to go ahead and show you what the book has. So this is our two trajectories, okay, in order to get to that same spot here, okay. So this is just using some type of graphing program, just like Excel or Google Sheets or something, to graph these equations. Okay. All right. Next, we need to touch on uniform circular motion, and we'll get more in depth with it later on in the course. But this is just kind of to get your mind rolling on it. Okay. This is a certain type of motion that where an object travels in a circular motion with a constant speed. Okay, so your speed will remain the same, but your acceleration may change. Okay, and we have centripetal acceleration, or the radial acceleration, which will always point in towards the center of the circular motion. Okay, so these are just diagrams to show you what is going on. Okay, so in A, you can see that we have some initial position vector, okay? And then after some time, we have a second one, and so we're able to describe that motion, okay? But again, our velocities will remain the same here, okay? And over here, again, our acceleration ports in towards the center, and we have that described here, okay? So our centripetal acceleration, A sub c, is equal to v squared over r, okay? And that's using this idea here that the acceleration is equal to the limit as delta t goes to 0 of delta v over delta t, or the change in velocity over the change in time, okay? And with some geometry, we can find that delta v over delta t is the same as v over r delta t, okay? All right, so with that, we're gonna do an example, okay? This is 4.10. A jet is flying at 134.1 meters per second along a straight line, and then makes a turn along a circular path level with the ground. What does the radius of the circle have to be to produce a centripetal acceleration of 1g on the pilot and jet toward the center of the circular trajectory? Okay, so jet is flying along and then gradually turns, okay, along, okay, that was terrible. Turns along this line. Okay, so they're going, and then it starts to curve, okay? So we want to know what does this radius of the circle, so we want to know r, to have an acceleration, centripetal acceleration of 1g, or 9.8 meters per second squared, okay? We have our velocity is 134.1 meters per second, okay? So we want to know r. So what we'll do is we'll take this equation here, a sub c equals v squared over r, and solve for that radius. So r then equals v squared over a sub c. So we can plug that in, 134.1 meters per second and then we square that and divide it by 9.8 meters per second squared. Okay. So let's put that in our calculator. 134.1 squared divided by 9.8. And we get our radius must be 1,830 approximately. And this is in meters per second. Nope, this is in meters. Whoops, sorry. It's a radius. Okay, so it's in meters. Okay, now let's think about this for a second. Does this make sense? Whenever you're doing a problem, you want to make sure that it makes sense. So if a jet is flying at this high speed, okay, well, it's high for us on the ground, but if they're driving at this speed, okay, to have to make a turn and maintain that same velocity, it'll have to be a pretty wide turn. Think about when you're driving, you have to slow down to make a turn, right? Turn right, turn left. You have to slow down quite a bit. So for them to be able to keep that same velocity and turn, okay, on this circular path, that'll have to be a pretty big radius. Okay, so this makes sense. All right, so we have some equations for motion for this uniform circular motion, okay? We have the position, velocity, and acceleration vectors, and these are going to now be in terms of polar coordinates, okay? When we get to 3 dimensions, it would be spherical coordinates, but for this, it'll be polar. Okay, so I'll write that down. Polar coordinates. Okay. And it is described as so. So the position vector is r of t equals a, where a is the radius of the circle and the magnitude of the position vector. Okay. Cosine of omega t, and omega is a constant. It is measured in radians per second. It's the angular frequency of the particle. Okay, so whatever particle we're looking at. So it's also described here. Omega equals 2 pi over t, where t is the period of motion, or the time to complete one revolution around a circle. Okay, so again, omega is a frequency, and t is the period of motion. Okay, so that omega t together is going to be theta, or the angle of the angle the position vector has at a particular time. So if you look here at this diagram, if we are looking at some position vector here at some point, okay, the angle here is described as omega t. Okay. So again, position vector r equals a cosine omega t I hat plus a sine omega t j hat. Okay. All right. And just to remind you guys that one revolution is 2 pi radians. You guys probably already know that, but just to kind of throw that in. Okay. The velocity vector will then be the derivative of this, okay, with respect to t. So you get negative a omega sine omega t I hat plus a omega cosine omega t j hat. Okay. Notice that the magnitude of the velocity vector is velocity, and it is a times omega. Okay. A times omega. The acceleration vector is the derivative of the velocity vector, okay, described here. And notice that the magnitude is a omega squared, and that makes sense because a of t is equal to negative omega squared r hat, or r vector.